Now, based on the shear stress expression, let's try to solve one example problem. So in this example problem, we're gonna consider a beam made out of like three wood films, and these three wood blocks are connected by nails, and nails are located every 25 millimeter, and thickness of the first wood block is 20 millimeter and width is 100 millimeter, and the second one has 100 millimeter height and 20 millimeter width, and you have a third one. So, and they are connected through the nail, and the beam is under 500 newton on point force at the right end of. Now, this problem asks what will be the maximum tau xy average out of the shear force 500 newton. And second question is asking what is the shear force on each nail. Okay, so you should have a nail like a dense enough. If you have nail like too far each other, you only have three nails to sustain the entire shearing force over the interface. Okay, so it's really important to determine shear force for each nail to design like appropriate distance between nails. Okay, so let's try to solve these two problems. And to answer this question, tau xy average maximum, we need to utilize this formula. Then when you look at this formula out of this problem, what you can see here is V is constant over the entire cross section, and I is determined by the cross sectional shape, which is this. Okay, so then you have qy integral and ty as a function of y. So when you consider qy integral, let's look at this. When you have this cross section, and this is y equals 0 position, and suppose that when y is like quite far from the center, you have to do this integral qy. You have to take this area, then you have very small area, right? So when y is close to like a 70 millimeter, the total height is 140 millimeter, because 100 20 20, right? And center is 0, so top is 70 millimeter from the centroid. Now when y is around 70 millimeter, you have almost 0 area A, so you have 0 qy. As you decrease y, if you decrease y here, then you have larger area. When you decrease y further, you have even larger area. So what you can expect is qy integral keep increasing when until y becomes 0. Now when y becomes y tilde becomes smaller than y, like when you have to integrate here, within this zone, you have y tilde, which is negative value, because you are integrating negative value, and dA is always positive because dA is the area. So you're gonna start to decrease the area, and as you do the cover the entire area, when y becomes negative 70, then you have to cover the entire area and this integral. And you can see that for this symmetric area, where you have same area top and same area bottom, and you have positive here, you have negative contribution here, and they're gonna completely cancel out. Okay, so this is the behavior of qy and q as a function of y. And regarding the thickness t, thickness was quite large, 100 millimeter when y is near the top or bottom, and y is near the center, it becomes 20 millimeter. So the distribution of ty would be something like this. When it's top, it's large. When it's center, t is minimum. So when q becomes maximum and t becomes minimum, t would become maximum. So you can expect that t xy will become maximum at y equals 0. Okay, so now you find the location. After finding the location, you have to obtain each value v, q, I, t at y equals 0 position. So let's try to do that. So let's do the integral at y equals 0. So y equals 0, the red area becomes this, and you have to do this familiar integral y dA. So instead of doing this integral as it is, what you do is you can use the intuition from our famous and friendly freshman physics. And freshman physics example, when we obtain the center of mass, this is what we do. And when we consider centroid for our ME231, this is what we have done. So we divide the red area into two parts. Each part must have the shape where we can obtain the centroid position easily. So for the first part, A1 part, we have 20 multiplied by 100 as a area, which is 2000 as an area, and the location of the centroid for A1 area is 60 millimeter from the centroid. It has 50 millimeter here, it has 20 millimeter here, and the location is exactly halfway through. So y1 bar should be 60. Okay, for the second one, you have 50 as a height and 20 as a thickness. So you have area of 1000, and the location of second one centroid is exactly halfway through, which is 25. So you plug in these numbers, and so that you can obtain Q at y equals 0 position, and T at y equals 0 position is 20 millimeter. So you obtained Q and T. Now it's time to obtain I. So when obtaining I, in previous chapter I introduced to you the usage of parallel axis theorem, but instead of parallel axis theorem, we can do this approach. When we consider the definition, the definition would be something like this. You do integral for this entire area, right? The I-shaped area. Now, what you can see here is you can convert this integral into three pieces. First piece is you consider the entire big rectangular shape like this. Now you take this little purple piece here and purple piece here. You take purple piece. Of course, the centroid position is halfway through. So if you do this integration over this rectangle first and subtract contribution of these two purple, from simple mathematics, it must be the same as the integral in the left hand side, right? And the reason why I took these kind of decomposition is it's quite easy to obtain the area moment of inertia for this rectangular shape. So for this big rectangular shape with thickness 100 and height 140, if you plug that into this equation, 1/12 is bh cubed, this is what you're gonna get. And we have exactly same two purple shape here and there, and each has like a 40 millimeter thickness and 100 millimeter height. So if you plug in here and multiply 2, because there is 2 contribution, then you will be able to obtain I. Now, having obtained the V, which is 500 Newton from which is given, and having obtained the Q and T and I at y equals 0 position, then maximum tau xy can be obtained as 2 to 3 kilopascal. So with this, we can answer the first question. Now, let's try to obtain second question. What will be the shear force on each nail? So, to answer this question, now we have to change the location of interest. So the nail have to sustain interface between this red block and the second block here. So what you have to focus is you have to focus the location of y equal 50 millimeter. So at y equal 50 millimeter, the Q integral becomes integral of this red block, and this integral over that red block becomes the area of this red block, which is 2000, 120, it becomes 2000 square millimeter, and the location of centroid is halfway through, which is 60 millimeter from the centroid. You plug in 60 millimeter, and if you do this integral, you're gonna get 120,000 cubic millimeter. Okay, so this is the Q integral at y equal 50 millimeter position. Now, having obtained the Q, you can obtain the small q, which is a shear force per unit length. Yeah, so you obtain the q. Yeah, this q is delta h over delta x. Yeah, so the every unit length, what you're going to expect is you're going to expect the VQ divided by I kind of force per unit length. And if you plug these numbers, yeah, out of the calculation, you're going to get 3.7 kilonewton per meter as the value for small q. Now, what you can see here is, yeah, this is your famous red block, and you have nails, and these nails located every 25 millimeter. So each nail should sustain 25 millimeter multiplied by Q force, so that you can sustain the shearing force over this interface. Okay, so if you multiply Q and 25, it becomes 92.6 Newton. Okay, so here we can have another design problem. So along this interface, yeah, there is 92.6 Newton force applied. If you divide this by area of nail, then it will give shearing force for nail, and this shearing force must be allowable shear stress of the nail. If nail is made out of steel, it should be allowable stress of the steel. Okay, so by comparing the material property of nail and the shearing stress applied for the nail, then you can say whether the design is reliable for, at least for the sake of the safety of nail. Okay, so with that we can answer the problem with two questions.